So I'm presenting this work on behalf of my colleagues, Kimberly Rogers and Mahu. We're presented with a problem. We have a lot of theoretically reasonable candidate parameters when we are specifying impression change equations. So this is a poor affect control theorist confronted with a laundry list of theoretically plausible options, right? So a little bit of theoretical background. I'm talking about the impression change model today. Okay, good, established. And what is the problem that we have? Well, I'm going to give you sort of the ideal case as a reference point, and then we'll sort of move from here. So when I'm estimating an equation using frequentist methods in a sort of nice universe, imagine that I have three covariates that I'm trying to predict. In this case, I've got age, gender, and race, and I just want to predict political party affiliation. And the wonderful thing about those is that those are exogenous by definition, and that they're time ordered nicely, right? Political party affiliation didn't come before I was born. Life is great. And I have data that's been nicely randomly sampled. So the likelihood that any one of these variables is being included by chance or erroneously is approximately 3% or a little under, right? So that's a nice world. That's not the world we live in, right? So this is just a slight reminder of what we're trying to do. We're trying to predict an actor's transient impression based on out-of-context meanings. And these out-of-context meanings are correlated with each other. And there's a lot of possibilities. So let's talk a little bit about the variables, the sort of model uncertainty problems that we have. We have 63 plausible candidates. Now we have some theoretical reasons to narrow down our list. So we're not going to do within element interactions. So I'm not interacting AE with AP, for instance. I'm not going to deal with fourth order effects, try interpreting those. Those are really difficult. And I'm only going to include third order effects for which there's a clear plausible theoretical interpretation. Other problems we have, though, is that we're going to be comparing nested models and that there's collinearity between the variables. And so our chances of including a variable by chance under these situations is relatively high. And also our chances of excluding a variable because of multicollinearity or including one because of multicollinearity is either inflated standard errors or because of suppressor effects is also high. So model selection challenges. I've got a lot of model combinations that I'm having to adjudicate through. Try doing that at home manually, right? I'd still be at home, right? And I've got a problem of potentially overfitting the model to the data. So I'm including variables that predict this data versus, and trying to make a parsimonious model to predict a lot of different situations. But I also have the challenge of losing explanatory power. Just because it's a small effect doesn't mean it might not be a theoretically relevant one. So I've got to adjudicate between all these different potential models. But the final thing is, I could possibly get a model fit with a different combination of variables that might have a very different theoretical interpretation, right? So if we go back to that old, to like a kind of stock sociological question, if I have occupation and prestige, and I have education, and I'm trying to measure something like performance, I might have different interpretations between education and prestige. So I have to have a model fitting strategy that I have confidence that when I ultimately come up with this model, that is a model that's meaningful because I'm rejecting other theoretical interpretations. Okay, so how have we done this in the past? We used stepwise regression, which is an automated procedure where we include a variable, we include it in our variable, so you can do forward or backward. I'm going to describe forward, but backwards just the same process in reverse. For instance, I'm predicting transient AE. I go, well, stability effect in the past, like that should be good. I put it in, I run a t-test on the thing. I get a probability, a p-value for it, and if it's below 0.01, I include it in the model. And then I add a new variable, I fit the whole model, and I remove variables after that fitting that have less than a 0.05 probability, right? And I do this as a wash and repeat process. The problem is that the model fit is sequence dependent, which means that correlation problem could come out and really have a problem, because I might have had a variable there by chance, and then it happens to be correlated with something else, and that might either include or exclude a variable that actually might be an important variable. And I'm never going to reanalyze these variables, right? So I'm going to have an order-dependent model at the end of the day that I don't absolutely know is the right model. So the next way of doing this is the ANOVA procedure, which was referenced earlier. So what I'm doing with the ANOVA procedure is I'm taking each potential variable that is trying to predict transient impressions, like in our case AE, and I dichotomize that variable, and I look at, is the between group difference significantly explained the variation in the dependent variable? If yes, yay. If no, then I'm not going to consider it. And ultimately going through this across all my possibilities, and then doing this for my 9 models, I get a single model solution. So I've only considered one solution because I either accepted or rejected. And so what happens is then we get very low false positive rates, because I basically have eliminated the possibility of having rejections due to correlation by treating each variable separately. And so the result of that is we tend to have small, parsimonious, stable models that we can have high confidence in. But the difficulty is that we can still be vulnerable. We've only considered one model possibility, so we still are at risk of type 2 errors. All right, so what are we doing here? This is a relatively high-level talk. I'm just going to sort of walk through this very quickly, but feel free to grab me. I'm here all week, as I say. So I am predicting the likelihood of AE being in the model as a function of some likelihood function given the model and the data. Now let me walk back this. So we have this problem about why is this called model uncertainty? I'm not certain about the chance of any one model being included or not included. So what I can do is I can first estimate how likely is the model going to be, how likely is the model? And really what that is functionally is like, what's the likely size of models going to be? So am I going to have big models or am I going to have small models? And then out of that set of likely models, then I can make my estimation of AE's probability based on the data and this likely set of probable models. And what that allows me to do then is I can estimate AE across the set of probable models and then average across that set to give myself a probability inclusion. So like how across all the possible probable models, not all possible, all probable, how often does AE show up, essentially? Okay, there's differences between the methods. High level, essentially getting this likelihood function in a normal distribution, you have to approximate it some way, because there's no closed form solution. So one way to do that is use a BIC score, and another way to do that is to use MC methods. BMA uses a BIC score to approximate that likelihood function and moves from there, and uses a set of rules to get rid of improbable models. So models that are 5% less likely than the most likely, they're not included for consideration. I basically explained the difference in the prior slide, but what we're doing here is instead of getting this likelihood function, instead of approximating it using a BIC score or using a BIC process, what we're doing is we're sampling from a posterior distribution to get this to recover this likelihood function, and then but to do that, and then we can solve this. But to do that, I have to assign a prior, and that prior basically says what are the reasonable size of these models. It basically specifies the range of the model sizes, and we can do that. There's many ways to do this prior, and I can talk about that offline, but they all do that by looking at the information in the data to make a reasonable approximation about what the right model size would be. Okay, data and methods. So we're trying to select variables, and we're going to look at a true positive rate and a false positive rate. And true positive rate, we successfully did it. False positive rate, we didn't. And we're going to look at what the coefficients resulting from that are going to look like. This, I'm running out of time. I created a ground truth model. I can talk about how I did that offline a little bit more, but essentially I selected some variables by random and made a synthetic equation, and then I tested the method's ability to recover that model, that underlying model. So results, we have the caption, the overall thing is that BMS and BMA outperform our past models. My recommendation would be BMS, particularly because of the lower false positive rate. We want to break that a little bit down further. You can see here, so this is false positive versus true positive, and this just gives us this distribution across possible models, how well the methods did. This is the bias in the estimates. Most of this bias is being driven by the various methods' ability to predict meeting the small coefficients. So if if the method was unable to recover or find a medium small coefficient, then that would be a bias score of its magnitude from 0. And so ANOVA has such a huge bias because ANOVA is essentially just isolating on the big effects. And the other methods do pretty well. And to say that when a method does successfully identify a covariate, the coefficient estimate is very similar. So that it's not a problem. Variable selection is really where the heart of the problem is. This is looking at the variance in the coefficients estimated. This is basically an extension of this variable selection problem, where if you're missing variables, then you're going to have more variance in your coefficient estimates, which is why ANOVA has this larger interquartile range. I want to say that ANOVA is actually a very good procedure, and that the results I'm showing here aren't doing it full justice, because what ANOVA's like special what ANOVA is particularly good at doing is these results are with lower correlation. We also have done data fit studies where we basically take the correlation matrix from real impression change data and then create a simulated ground truth model. In those instances, BMS and BNA still outperform ANOVA, but ANOVA was a real theoretical contribution.
So basically, in real data where there's much
your chance of
linearity, ANOVA is cutting through that.
Right. By basically considering each one of those variables separately, you're eliminating the ability of multicollinearity to reject a good predictor. Okay, so what this is doing is it's showing the distribution. Methods that are winner methods and coefficient estimates should be away from 0 and should have tighter distributions. If they have wide distributions, it means that we are having a lot of variance in our coefficient estimates, and if they're focused on 0, that means we're missing these coefficient sizes, or that we're missing these variables. On the bias scores, what you want is you want stuff close to 0 as possible, right? And you would like a nice, you would also like a nice tight distribution. And what we see comparing these two methods is that BMS and BMA have distributions that are more focused on zero and tighter distributions, and then the coefficient estimates that they have more distinct distributions not hovering on zero. All right, theoretical implications. Yeah, all right. These are the effects that we talked about earlier, which are super important, and it would be fun to talk a little bit more, but running out of time. The end all story is that not only is it in this data, we went back and used NC78, and we said, well, if the method that we use matters, how does it matter? And the way that we assessed how it mattered was, to what extent could we recover theoretically relevant events versus basically covariates for which we have no theoretical interpretation. And the end story is that the Bayesian methods, particularly BMS, were able to recover more theoretical events as compared to atheoretical events. So this is the ratio of theorized events to atheorized events, and BMS had a higher ratio. Of course, one would be that you're equally likely to get an atheorized to theorized event, and things that are higher, you're getting more theorized to atheorized. Discussion and conclusion. All right, so based on these findings, I recommend MC methods of Bayesian model averaging. Bayesian methods provide more levers. I'd love to talk a little bit more about that. Where I think the future is, as much of this conference is going to talk about, is the way BASAC does things. And what I mean that particularly is it would be good to move away from using point estimates to actually estimating, as BASAC does, impression change using the distributions of the concepts, which we did not do here. The challenge to doing that, and a thing I'd love to talk on Saturday about with smart people, is that some of the assumption that the concepts distributions are normal are not always applicable, and that they're patterned by institutions. And for more on that, talk to Brent. Okay, thank you very much for bearing with me.